Hello and welcome to overview of course content for soft robotic or MTRE 6740. My name is Amir and in this semester I will teach soft robotics as a course in our master program here at Kansas State University Department of Robotics and Mechatronics. Soft robotics is an emerging field of research which has a great potential for interfacing delicate objects and providing safe interaction between humans and robots. Throughout this course, we will study different soft actuators and sensors, such as pneumatic soft sensors and as well as electroactive polymer actuators. The course will be delivered online and it would be asynchronous course with optional meeting times. Also, every Friday from 4 p.m. to 5:30 p.m. we will have a live lecture session that you can ask your questions about lecture notes and also about the assignments. During the week you should watch the lectures online at your own pace and also submit all the required assignments and homeworks. So here is what we will study throughout this semester in this soft robotic course. We'll start with electroactive polymer actuators. We'll start with linear model of these systems and we'll discuss different fabrication methods for these actuators. We'll talk about soft pneumatic actuators and a brief introduction about modeling and fabrication of those actuators as well. Then we'll start working on kinematics and we'll start with a brief introduction into kinematic modeling. Then we'll start to talk about kinematics of soft serial robots. Then we'll continue our discussion about parallel robots. We start with rigid parallel robot mechanism and then we'll extend it to soft robots. In particular, we studied the kinematics of soft 2 degree of freedom robot, soft delta robot, and soft Stewart mechanism. Toward the end of this course, we'll study the rigid finite element and nonlinear deformation of the beams, and we'll have several examples where students will compare the rigid finite element with the nonlinear deformation of the Euler-Birolini beam models. Okay, so now we are going to have a brief overview of the chapters that we will cover throughout this semester. So one of these chapters would be about Polypyrrole bending actuators. They are also known as electroactive bending actuators. We will study how to model the deformation of these systems. Essentially, these systems are polymeric material that when we apply electrical voltage to the system, they deform. So we'll come up with different mathematical model to predict the bending and deformation of this system. We will also discuss the fabrication of these systems and how we can manufacture these actuators. Okay, the next chapter would be about kinematics. So the kinematics is the science of studying the deformation or motion without considering the forces that result those motions. So we will start with a serial soft robots. As you can see here, I have one example of the soft robot, which is a L-shaped soft robots, and it has small deformation. We can also have soft robotic systems that undergo large deformation, as this example here. Actually, this one is about the 2 degrees of freedom soft robot, soft serial robot, and here we show its workspace when it bends over 180 degrees. Okay, the next chapter would be about kinematics of soft parallel robots. We will start with the kinematics of soft rigid robots and then we will extend it to the parallel robots. As an example here, we can see a 2 degree of freedom soft parallel robots. As you can see, the blue links are the soft links that actually deform and bend and cause the end effector to move in a linear trajectory, circular trajectory, or any arbitrary trajectory. And throughout this chapter we will study how to understand the kinematics of this system and what type of deformation in the blue link will result in a linear motion versus a circular motion or elliptical motion or any arbitrary trajectory of interest. Next, we will extend our study to soft parallel robots with 3 degrees of freedom. In this case, we will study the kinematics of a delta robot. Delta robot is a well-known parallel robot that can be used in different manufacturing tasks such as pick and place. We will study with the kinematic of a rigid delta robot, and then again we will extend it to a soft parallel version of it. Here you can see the prototype of the soft delta robot that can uh, create 3 degrees of freedom in X, Y, and Z motion. So we will drive the kinematic model and we will perform different simulation for different scenarios. As a final example on kinematics of soft parallel robot, we will study the structure of the Stewart mechanism. A Stewart mechanism has 6 degrees of freedom, meaning that the end effector can move in X, Y, Z direction and can rotate in roll, pitch, yaw angles. Now we'll start with the rigid mechanism and then we'll extend our analysis to a soft version. Here you can see the soft version, which the blue links are the soft arms that actually bend. And we will develop models that can predict the motion of this system in different trajectories. Here you can see a linear trajectory, horizontal one, as well as the vertical one and a circular path. And finally, we will study rigid finite element as a last chapter in this course. As you have seen so far, soft robotic systems most of the time undergo large deformation. That makes the system nonlinear, and we cannot use the linear systems that we have developed in previous courses. So, we will introduce rigid finite element as a method to take into account large deformation in the structure of mechanical system. And we will study this example for the nonlinear Euler-Bernoulli beam model. We will have different loading on the system and we will obtain the deformation. With that being said, thank you so much and see you soon in the next presentation.